In this video, we will discuss the short-run production. In the short run, at least some inputs cannot be changed. To fix ideas, let's assume that capital is fixed at some level K bar, and the firm can freely choose the level of labor. In this case, the short-run production function will look something like this, where the level of input is fixed at K bar, and we're freely able to change the level of labor input L. Sometimes, when labor is the only relevant variable that the firm can choose, we'll call the production function the total product of labor. The term total product may seem a little strange, but it is called total relative to these two following terms, marginal and average. Or more specifically, marginal product of labor and average product of labor. The marginal product of labor measures how many additional outputs each additional unit of labor input can bring. So the marginal product of labor is just a derivative of the total product of labor with respect to labor. The average product of labor measures how many units of output does each unit of labor produce on average. So it is calculated by dividing the total amount of output we get when we use our units of labor. Let's look at an example to see the differences about these two concepts and the relationship to each other. Suppose that we have a production function that takes this particular form. And in the short run, let's assume that K is fixed at K bar, which takes a value of 10. Now let's try to calculate the marginal product of labor and the average product of labor. First of all, knowing that K takes a value of 10 as being fixed, we can plug in this value into the production function, and that will give us the specific total product of labor. How would you calculate the marginal product of labor? Can you give this a try? The algebra is very straightforward. The exercise is really in thinking about the definition intuitively. Please pause the video and give it a shot. Well, to calculate the marginal product of labor, we just take a derivative of the total product of labor, which is a production function with respect to labor. And with K fixed at 10, the result is just 200L plus 10. We can also calculate the average product of labor. How do we do that? Can you pause the video and give that a try as well? Well, the average product of labor is the total product divided by the amount of labor used to produce that particular amount. So we have the following expression. With K fixed at 10 units, the average product of labor is just 100L plus 10. These expressions of average product of labor and marginal product of labor may seem somewhat abstract because they're functions of L. This is totally normal because we haven't told the function how much labor we actually used in this production specifically. So the marginal product and average product may very well vary as the amount of labor used is being changed. And these functions of marginal product and average product captures how these measures vary as L changes. Now let's take a look at some graphs to see this point more clearly. You probably have seen these graphs about marginal and average from the principal economics classes, but it is useful to have a refresher here. On the top panel, we plot a total output as a function of labor inputs. And we can see that their relationship is not linear. As we use more units of labor, the output level increases, but the rate of increase changes a lot. When we have very few units of labor, putting in more labor increases the output by very small amounts. but then the additional labor units become more and more productive. You can think of this as a business that requires a certain amount of labor to function efficiently. If you think about the large restaurants, having one person restaurant running between the kitchen and the tables just isn't very efficient. And adding a second chef can be tremendously productive in the kitchen when the chefs can cooperate with each other. Because the marginal product of labor is just the derivative of the total product of labor. So graphically, the value of the marginal product is just the value of the slope of the total product curve. This is plotted in the lower panel here on the screen curve, which indicates the marginal product curve. In other words, the marginal product of labor is very low when the amount of labor input is low. But it gets higher and higher and higher as L increases. However, the rate of increase in the total product slows down at some point, and eventually even becomes negative. Think about the restaurant example again. As you add more and more waiters and chefs to a restaurant, they're probably still productive. But the change in output is unlikely to be comparable to a second person in the kitchen. We see that on the graph here, once the level of labor passes point of A, the total product curves start to bend downwards, and the rate of increase starts to slow down. In other words, the marginal product labor starts to decrease, although the marginal product is still positive, so the total product is still going up. And at some point, adding more people or hours can even become counterproductive. For instance, the facility may get overcrowded, or coordination can become exceedingly difficult. On this total product curve here, once the level of input of labor is beyond this point C, more labor is counterproductive, and the slope of the total curve becomes negative. So the marginal product becomes negative. Well, of course, we're plotting it with dashed lines here because no sensible manager will ever go there. But we do know this is a possibility. Now let's think about the average product of labor. How does the average product relate to the total product curve? Well, the value of the average product at a particular level of labor is measured by the slope of the ray from the origin connecting to that particular point on the product curve. For example, if I draw a ray from the origin and connect it to this particular point A on the total product curve, then the slope of this ray measures the average product of labor at this particular point, or in other words, at this particular level of input of labor. Why is the average product the slope of this ray? This is because if we write down the average product again, it is just the total product divided by the amount of labor input, which is the y-coordinate at this point divided by the x-coordinate at this point. In other words, this is just rise over run of this particular ray shooting from the origin to this particular point on the total curve. And the slope of this ray is exactly the average product of labor. Now let's look at how the average product of labor changes as the amount of labor input increases. If we draw a slope from the origin and start to point at different points along this total curve, we realize that the slope of this ray starts out to be relatively low, and then it gradually increases, becomes steeper and steeper and steeper and steeper, passing point A and still getting even steeper, up until point B, where the slope of the ray reaches the maximum, and then it starts to become flatter and flatter, meaning the average product labor starts to decrease. And this is exactly what the blue curve on the lower panel here indicates, which measures the average product of labor. It increases before reaching the point B, and then starts to decrease once labor goes beyond this point. An interesting question to ask is, how does the average product curve relate to the marginal product curve? An interesting point to notice here on this graph is this point B. At point B, the ray from the origin is precisely the tangent line of this total product curve. This means that the marginal product and the average product take exactly the same value. If we look at any point towards the left of point B, let's say on point A here, the tangent curve at point A is steeper than the slope of the ray from the origin. If I draw a tangent line at point A, it will probably look something like this, which is steeper than the ray from the origin. So the marginal product of labor at point A is higher than the average product labor at point A. And you can repeat this exercise for all these different points before point B, and you will realize that it is always the case that the marginal product is higher than the average product. On the contrary, once we passed point B here, the tangent curve becomes flatter than the average. If I draw a tangent line for the marginal curve here, it probably looks something like this at this particular point. But if I were to draw a ray from the origin, then the slope will look something like this, which is steeper than the marginal curve. Therefore, the marginal product becomes smaller than the average product once the level of labor goes beyond point B. And this is exactly what's indicated on the graph in this lower panel here. Once we pass labor at point B, what happens is the marginal product labor becomes lower than the average product labor. To summarize all these observations in the graph on this lower panel, the marginal product labor increases, reaches its peak at point A, and then starts to decrease. The average product labor increases and reaches the peak at a later point of point B here. And this is where the marginal product and the average product coincide. And once we move beyond point B, the average product also starts to decrease. One pattern we might have realized is that it seems like the average product increases when the marginal product is higher than average, and the average starts to decrease once the marginal becomes lower than the average. It turns out that this is not coincidental at all. In general, the relationship between marginal and average follows a pattern. The pattern is not restricted to the graph we draw here, or restricted to the product of labor. The pattern is that the average increases whenever the marginal is higher than average, and decreases whenever the marginal is lower. So it must be the case that the average will reach its peak or trough when the marginal is equal to the average. The general intuition is actually quite straightforward. Think of the example of GPA that we're all very familiar with. Let's say that I now have a current GPA of 3.0, and GPA is just an average of grades. And now I'm going to get a B+ for this course, which will give me a marginal grade point of 3.3. So in that case, my new GPA is going to be higher. And this is because my marginal grade is pulling up the average of 3.0. On the other hand, if I get a B- next semester, with a marginal grade point of 2.7, then I would expect my GPA to go down, because in that case, my marginal value is going to be lower than the average. And that's exactly the same idea here with productions. If the marginal is higher than average, the average must increase, and when the marginal is lower than average, then the average must decrease. Here we offer a more formal mathematical argument in the case of marginal and average product of labor. The proof verifies our intuition and also helps deepen our understanding about these two important concepts of average product and marginal product. The statement looks a little bit scary, but it just describes our previous observation about the marginal and average products. The statement says that if we have a product function f, which is a function of labor input L, and if the function is differentiable, which means we can take a derivative of it to find the marginal product of labor, then the average product will increase if and only if the marginal product is higher than the average. As a result, if the marginal product is higher than the average product when the labor input level is small or the output level is small, then the average product will reach its peak when they're equal to each other. Now let's look at the proof, which only takes one line. We're interested in how the average product of labor changes as the amount of labor increases, whether it will increase or decrease in particular. So now let's take a derivative of average product of labor with respect to labor. By the definition of average product of labor, it is just the total product divided by labor. So we just take the derivative of this ratio with respect to labor, or L. Because both the numerator and the denominator are functions of L, we can use the quotient rule or the product rule, whichever you prefer. Here, I'm actually using the product rule by seeing this ratio as a product between f of L and 1 over L. So the derivative of the ratio is equal to the derivative of the first term in the product, which is f of L with respect to L, times the second term, which is 1 over L, untouched. And then plus the first term, untouched, f of L, times the derivative of the second term, which is 1 over L with respect to L. But then the derivative of 1 over L with respect to L is minus 1 over L squared. So then we have the second term here with a minus sign. Now with this expression, I can factor out the common term of 1 over L. Now what I'm going to have left over is the derivative of f with respect to L on the inside, and in the second term I'm going to have f of L divided by one of the L's, because the other one is pulled out. So within the parentheses, we have the derivative of the total product with respect to L, which is the marginal product of labor. And the second term is just the total product divided by L, which is the average product of labor. Now let's try to think about the sign of this expression a little bit. We know that 1 over L is definitely positive, because L is just a positive amount of labor input. So the sign of this expression, or the sign of the derivative, just depend on these two terms within the parentheses. If the marginal product is bigger than the average product, then the derivative is going to have a positive sign, meaning that when we have higher labor inputs, the average product is going to increase. Whereas on the other hand, if the marginal product labor is lower than the average product, then the sign is going to be negative. In other words, average product is going to decrease if the marginal product labor is less than the average product labor. And that's exactly what our intuition says. These 2 bullet points just summarize what we were discussing, and the term IFF is denoting if and only if as a shorthand. In particular, if the marginal product is higher than average product when the input level L is small or the output level Q is small, which is referring to this part of the graph. So if we start out with the marginal product higher than the average, then the average will get pulled up initially and then decrease once the marginal product falls underneath it. In that case, we're going to see a peak on the average product curve when these 2 values coincide at the level of B. I think this proof helped us understand the average product is an important concept, but it is just a function based on the total product, or production function. We will see that this intuition about the marginal and average values reappear in a slightly different way when we discuss costs. An important concept related to the marginal product is the law of diminishing marginal returns. We can motivate the idea by thinking about a few different examples. If you grow herbs in a backyard, a windowsill, or balcony, then you will start by using the best spots you have, where perhaps the sunlight condition is most ideal for that plant. As you grow a second pot of the same plant, or third, or fourth, those plants will have to take less and less ideal spots. So at some point, regardless of how you double your water, your seeds, your fertilizer, and all the other inputs, the output is unlikely to double. As another example, if someone opens a coffee shop in town, they will probably pick the most favorable location. But as they expand to more locations in town, it is inevitable that the locations become less and less suitable for coffee shops. So although you can invest in the same store design, same layout, same size of staff, the revenue may not be as good. In other words, doubling the number of stores by doubling investments and labor may not yield double the output. We can also think about a third example. In a large manufacturing factory or large business chain, coordinating tasks among larger and larger teams gets increasingly challenging. So at a certain point, doubling the size of the plant and the size of the employees just won't double the output. Well, the point here, through these examples, is that some essential inputs are limited. So as you double other inputs, the output just cannot double. This observation is generalized and summarized by the law of diminishing marginal returns. Specifically, the law of diminishing marginal returns states that the marginal product of an input, let's say labor, should decrease when the amount of input increases and when it gets sufficiently high. In other words, if we take a derivative of the marginal product, it should be negative when the input is sufficiently high. Now, because the marginal product itself is a first-order derivative of the production function, so the derivative of the derivative with respect to the same variable is just a second derivative of the production function with respect to the input. So the law of diminishing marginal returns in some ways just says that the second derivative of the production function should be negative. Graphically, this property means that the marginal product curve has to eventually decline and bend downwards faster and faster. This means the curve will be concave when the input is sufficiently large. For the total product curve we saw previously, it becomes concave once the level of labor goes beyond the point at point A here. This is also where the marginal product curve starts to decrease. Note that the law of diminishing returns does not require the marginal product to be negative everywhere. It only says the marginal product should become negative when the input becomes high. When the input level is low, the marginal product can very well be increasing. If you think about a restaurant hiring the first waiter in addition to the chef, or an individual mover hiring a second worker to work together, the second unit of labor could very well have a higher marginal product than the first. The statement simply says that this type of feature is uncommon when you already have a lot of this input. In many applications, the models simply assume a concave production function. You can see this as a modeling choice that ignores the initial phase where the input is very low and the marginal product increases with the input. This is appropriate if the firm you model is already at a relatively large scale, but it may not be as appropriate in modeling mom and pop shops. A strictly concave production function captures the essence of the law of diminishing marginal returns. Each additional unit of input produces a positive amount of good, but its marginal product is becoming less and less. Now let me conclude this part with two notes. First, the model assumes that the production function is continuous in the inputs. This means as you add more and more labor, each unit of labor brings you a steady amount of output. But this is not necessarily true in reality. If you think about the research input and output in developing a new medical treatment for cancer or coronavirus, the outputs come through a series of discoveries or breakthroughs. So if we think about a production function, it probably looks something like this, which is called a step function. For a step function, there is no marginal product for a very long period of time as you add more and more and more labor. And as this team works even longer times, perhaps they found one discovery or one breakthrough. So the marginal product is zero in all these hours leading up to it. But then there's almost an infinity marginal product at this jump, and it becomes zero again. And another huge jump, and the marginal product becomes zero again. So can we still use the model for applications like this? Well, yes, we can. This is because the decision problem about inputs usually take place before the production actually happens. So there is always a forward-looking element to this decision. In other words, it is appropriate to think of the input as increasing in the probability of a discovery or a breakthrough. In this regard, we can model the probability of producing a breakthrough as the output. Then the production function becomes continuous in the input again as we put in more and more and more hours, or having a bigger and bigger and bigger research team. The probability of finding a discovery steadily increases. Our second note is about the nature of diminishing marginal returns. Just like the law of demand, the law of diminishing marginal returns is a stylized fact that economists think is present in most situations. So it will be very useful for modeling choices if our models have this kind of properties built in. However, it is not a direct assumption that we impose on the model of the firm. In the next video, we'll turn to look at the long-run production scenario, where both inputs, capital, and labor are adjustable.